Does that work, or am I only in one side? Someone tell me if I'm mono. Awesome. All right, great. It's totally not one of my streams without issues in the beginning. My face was too dark, and then I was muted. So great. Anyway, hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. It's been a long time since I've both streamed a hardware episode. So I want to do a quick kind of recap. But by the way, first of all, hi to guys in the chat. Really good to see you all again. Disused, Freeful, Alkama. Sorry I'm not going to Evoke, man. And thanks again for the sub. I really appreciate that. Devoid, Mr. Liquid. Saya Attack or Saja Attack? I don't know which one that is. D7 Samurai. By the way, it's not intruding if you want to come say hi to Suskugen, but I appreciate the consideration anyway. Fuking Supa. It sounds Danish to me. Let's see if I missed anyone. Repnop, Moveaway00, Defram, Wizardtobe. Good to see you all again. Yeah, so like I said, it's been a while since I've done one of these streams. I think it was last year, in like February and March, I started this project, which I call Xenowing, which is the most 90s game console name I could come up with for anything. The goal, just to give you like super high level overview, I have this FPGA board. It's a Max 10 development kit. It's better if I pull up a picture than if I show it to you. It's an Altera board that I bought in like 2015, and it's okay. It's got all the stuff I need. And what I want to do is I want to make kind of a late 90s era video game console kind of thing. So this is what the board looks like. It's got an FPGA on it, and we're doing everything on that FPGA. Now, what that exactly entails is kind of up for debate, because I kind of just wanted to see where we got. Oh, how's it going, Raven? I didn't realize. That's awesome. Freefall, got to make a demo for it too? Yes, I absolutely do. Yeah, so the main kind of requirements that I wanted a risc-v CPU, and I wanted some basic GPU that involves streaming out pixels to HDMI. This board has an HDMI transmitter chip here, so if you send some I2C commands to it, you can turn it on, and then you can just send it pixels. And that works just fine. There's also a UART transmitter, which I think is this one, the FTDI chip. This gives us some input and output. Right now I'm using the output for like put S, so we can actually see what's happening on the CPU on the board. There's also a receive here, which I implemented a ROM reloader for, because compiling the hardware and getting it like on the actual FPGA takes like 10 minutes right now. Yes, that's actually ridiculous. And this is Taiwanese dollars. Is that what that is? Somehow I ended up at terrasec.com/TW. That's great. Anyway, yeah, I also I was doing ROM reload so that we could get the thing on there, or get the hardware on there, and then update software really quickly, which I suspect we'll have to do when implementing like a basic rasterizer, which is the other thing I wanted to do in the GPU, is a little rasterizer. But I was going to implement that in software first and then kind of move bits over into hardware. In addition, I want to have some basic sound output that just outputs some waveforms. And originally this also has DDR3 memory on it, which actually like half the design right now is a generated DDR3 driver, which is kind of funny. Anyway, about as far as I got with that was I implemented a working RISC-v CPU, and I did it in kind of a bad way. I did it in a way that appears to work, but I think there's a bug somewhere, and it's either in that or in the memory bus, the main system bus. I'm not actually sure. So I'd like to kind of redo the CPU a little bit, just to get it. First of all, I know that the CPU is going to be really slow, because the approach that I took essentially is a state machine approach, which is really simple because you don't have hazards, but also is really slow. And I want to split up into different hardware units for different pipeline stages, even if we don't actually implement pipelining, because then we can still avoid the hazards, but we end up with an overall simpler and ideally smaller design. It might not actually end up being smaller, at least not in terms of register count, but I think it will be simpler to understand. And then I still want to hook this up to some formal verification suites and make sure that that's actually correct when I feel like that's a little easier to do. So I think that'll be good. I think that's also a good way to sort of get back into the project. which is what I want to do lately. Because for those of you guys that don't know, I changed jobs actually twice in the last year. CodeRub, thanks for the follow. And the job I'm working at now is very hardware focused, so this is kind of in my head a lot now, which is really nice. The D10 Nano Mister, yeah, so I am vaguely familiar with that. I know people are running a lot of emulators on that, or implementing a lot of old school systems on that. So I think the core of the thing that I'm designing should be able to work on there. But the amount of things that you need to do to make it work with the peripherals on that particular board, of course, is going to probably vary. And I don't really know how much work that actually is to port an FPGA project, because, like, again, the core of the computer itself and most of the logic stuff is totally portable. There's nothing specific to my hardware about that. But then all of the bootstrapping, of course, is there's some, I don't know if bootstrapping is the right word, but hooking the computer to the outside world, because we expect that there's memory and that it follows a certain kind of interface, and we expect, actually that's probably the main thing. There's also a UART transmitter and receiver, but you don't need to hook those up. This will operate fine without it. And of course, we will be making this specific to this kind of transmitter chip. But again, that stuff could be swapped out, but you would need different drivers then in the software as well. So I don't really care to do a lot of that porting work, but I'd be happy to help anyone else if they wanted to. But again, the project's still so young that I don't think it's really worth considering. But again, the core design will, of course, be totally portable. There's nothing super special about that. Is that kind of enough of an intro, or should I do more? I don't remember all of what I said right now. I've got a lot of things floating in my head these days, which I'm really enjoying, but yeah. Also, sorry it's been so long since I streamed. I got really busy this summer, and it's been a really good summer, a really good period in my life the last few months. But I got engaged. That's pretty exciting, among many other things. So very happy about that, but I also really want to get streaming again. I've been really, really itchy about this. So good to be back and good to see you guys again. Hey, Aaron the German. I really liked your Break the Encoder intro, by the way. ST47IK, how's it going? Wootness, what's up? Hey, Try Guy. Krachev, put us in the FPGA, yeah. Hey, Try Later. Yeah, thanks, Mr. Liquid. Enjoy some nerdgasm. So when I implemented the CPU, I can let's do some paint. So effectively, when you're going to implement an instruction, for example, like a load, I should try to use RISC-V conventions too. The reason, by the way, that I chose RISC-V for this, and I'm implementing everything from scratch, so I'm implementing my own RISC-V core, and this is kind of what I hope to get back into today. RISC-V is, of course, an off-the-shelf ISA, which is what I wanted. And let's see. RE32I base instruction set, load and store instructions. Let's see, where's a load? I think it's just called load. So you do like load, and I guess you'd have a destination. It's been so long since I've looked at this. But let's say this was, is it X? X2, and I guess you have someone help me out here. I'm such a pro. And then where would you load this from? I'm guessing you would load it from a memory address, right? Oh yeah, it's a base, and looks like there's a width in a few of these bits as well. Aggressive says, which HDL are you using? I'm using System Verilog. Let me actually just OBJ dump some of my ROM. That'll help. RISC-V, and then some other stuff. Not in bed. OBJ dump, and we'll do rom/rom.elf, right? And then we can just disassemble this. Let's find a load. Do we have a load? Okay, we don't need to do a load. We can just do like a load upper immediate. Let's do that. LUI. And then this is going to have, in this case, T0, because I guess it's using a alias for that register, and then some operand, so 0x5, for example. This is an instruction. So this needs to go through several stages in order to actually execute this. And what we want to do several different, or I'm getting a little distracted here. So we need to first load this from memory, which is called the instruction fetch. So we're going to have like an instruction fetch stage that this will go through. And this is essentially getting this instruction into our processor. And as you can see from this, it's encoded something like this. Of course, we'd have a different constant here, so that would look a little different, but there we go. And then what we're doing is we need to kind of decode that. I think the instructions in RISC-V are so simple that we may not even need like a decode stage, but what a stage that I'm probably going to have is, this is actually probably going to be instruction fetch issue, and then I'm going to have an instruction fetch wait, I think I'm going to do. Because the way that the hardware bus is in this hardware, and this is a consequence of the DDR driver that I'm using, the memory bus, you kind of issue a read, and then you kind of wait for data to come back. And so we won't have it within the same cycle. So we need at least a way to stall. And I think splitting this up into 2 stages is the easiest way to do this. It might not be, but we're going to see. So this is kind of collectively an instruction fetch stage, but I think it's going to end up being 2 stages. Let's see what other states I kind of had for this, which is kind of going to be a good way to get into this, I guess. I also had like an initial setup and stuff, but we'll get to those because some of this will be a lot simplified, I think, when we do this. Okay, so it looks like I did have a decode stage. And actually, I wouldn't be surprised if that was this instruction fetch wait. So let's actually call it like this: instruction fetch and then instruction fetch, or actually decode. And then after that, we had, I probably folded that in with execute. We'll see if that's something that makes sense for us to do or not. Then we had a memory load stage, or I guess this would be mem in the classic RISC parlance. So it's kind of doing reads or writes, and then finally write back. And write back. This is kind of simplified. It's not necessarily the classic RISC pipeline stages that you might be used to. We can call this EX as well for execute. But generally, if we free full, yes, it totally is. These are kind of the different stages that an instruction has to go through to be retired. So we go and fetch. So we go and fetch the bytes that represent the instruction. We decode and kind of execute that. And then if it's a load or store, we might have another stage where we're going to actually hit memory there. And then finally, we're going to write back the result to the relevant registers. In this case, we're going to write this value into this. And then in this case, the memory stage would be kind of not used. So generally in a RISC implementation, a simple RISC CPU, you're going to have these different stages, and there's going to be different hardware units that are going to execute all these different things. And then in between here, you're going to have registers that sort of store enough state for each pipeline stage to operate independently. So the idea is that this instruction would come in here and then be put into this register. And then on the next cycle, it's going to go through this pipeline stage and go into this register on the next cycle, and so on and so forth. And the idea behind that is that then you could pipeline execution of these, because all these are running in parallel on top of different instructions. Now that's pretty simple if your instruction stream is perfectly linear, but of course in a real instruction stream you have a lot of branches, and you have things like the write back stage. If you do like this load, and then you do like an add that uses T0 as an argument, then we need to make sure that this part where it's executing for this instruction doesn't happen before this one's write back. We call that a hazard because there's a data dependency here. And so then you need to put a bunch of stalls in the pipeline as well. So I was hoping to just kind of avoid a lot of those issues. You either stall or do forwarding, like Rachev mentions as well. And I just decided that I don't want to deal with that. And so what I did is I implemented the whole thing as a state machine. So we would go through these different states and then do different things in there. The nice thing about that is, yes, we avoid those issues. The downside is, of course, we get worse performance. But I don't really care so much about that because I think the CPU is going to be more than fast enough for what we need. Eventually, by the way, I do want to do proper pipelining, but we'll get to that. I want to get a CPU that's working and robust and then kind of work on the other parts of the system before coming back to that, because I think that's going to be the most fun thing. By the way, yes, Mr. Liquid, that Ben Eater series is so good, and that's another reason why I'm really inspired to work on hardware right now, is because of his videos on making a graphics card came up, and I found that really inspiring. And then, anyway. Besides the point. But there's kind of another way to do this, which is where we still implement all of these as separate hardware units that in theory could operate independently, but then we just have some control logic out here that's only going to activate one at a time. And I think that's going to be overall the simplest way to look at this, and it's going to be sort of more future-proof. So by the time we actually want to implement pipelining properly, then at least we have that part done. So I want to start by kind of basically doing this from scratch, or at least looking at what we've done already and making it simpler by moving to this. So that's kind of what I want to do. Before I get to that again, you can see this in a lot of the other videos, but I want to talk a little bit about what I have so far. And effectively what I have is the xenowing repo. I can link to that. And it has pretty much everything in it. And this has some documentation on like what my memory map is currently. It has some missed stuff, so like a ROM loader thing, and then there's this converter tool that converts the ROM into the format that my FPGA tools need. There's Quartus stuff, which contains tests, or actual Quartus project files. I'm using an Altera board, so that's why it's Quartus. And then I have like just a DDR3 test, and I also have a test for the actual hardware that gets the hardware running on there. Then I have a ROM folder, which contains the startup ROM right now, which is actually written in C, which is one of the reasons why I chose RISC-V. It's actually easier, I think, to implement your own CPU if you just want to make it really minimal. But the point of this is that I wanted to work on more of the other parts of the hardware. I wasn't actually that interested in making a CPU, or at least not as interested. So I wanted to use something off where I have a C compiler, and I want to have just all that made for me. I don't want to write all this in assembler. So that's kind of the advantage. And then that, of course, just needs a little bit of startup stuff that's not that bad. And then I think I have a linker script in here, too, that just kind of makes it a flat binary, so I can just put it in ROM. In addition to that, we don't have like a proper C runtime or anything. In addition to that, I have the RTL, which is the actual hardware itself. And I have the sim folder, which contains some wrappers. So I use Verilator to generate some hardware or some software simulators for some parts of the hardware. And then I wrap those up in a library, and then or in a program, and then I have like a little Rust DLL that loads and sort of calls into. So I can sort of write tests in Rust that go against the hardware, and that's just for my own fun. In particular, there's this xenowing test thing here, which will load the ROM and sort of run the thing. And it'll run it a number of cycles, and like if the LED registers change, then it's going to output that to the terminal. And again, what that really gives me is just kind of this full environment where if I do make test here, it will actually run my ROM program in the simulated hardware and tell me any output that happened. Of course, this is incomplete because, like I said, I have UART that should be printed here as well, but I don't have the UART receiving simulator, so I need to do that at some point. It's probably something we should have done before this stream, but whatever. And then I have this trace directory, which only happens when you actually run this test, because it also it dumps a trace. And if I pull up GTK Wave, which is just a generic waveform viewer, we should be able to see basically whatever within the actual hardware. Here, GTK Wave, and then I can open the actual test trace. Takes a while to load because it runs a lot of cycles, and this captures everything. And then, so if we can go into the xenowing, for example, and go into like the CPU, and we can see I don't know, just pick any one of these. Append all the ones for the CPU. Does that work? No, it doesn't. Let's look at the UART transmitter or something. Just grab everything, put it in there. We can see the state of all these signals over time, which is kind of cool. And this, of course, is very useful for debugging, to say the least. So yeah, so we have at least a way to work on all this. Maybe not the best way to work on a lot of this, but it seems to work. So that's kind of where we're at. And we've got a lot to do here. But I think this is pretty fun. So to dive back in, I just want to show a little bit more of the code here for the CPU. I said that I implemented it all as a state machine. There's a couple additional units that I've kind of split out of this. Like the register file is kind of its own thing. And what I actually do is I have, I expect an external ROM to be hooked up to this, or external RAM, I mean. Or no, the registers are all here. Okay, yeah, so I think I worked really hard to get the synthesis tools to infer a block RAM here by making sure that we actually have 32 words, even though we actually only need 31 because register 0 on RISC-V is always 0. And it looks like I'm able to write any of these. Oh yeah, right, there's not 0 here. I might actually make this so that you could write any of them, which would remove some of this logic. Because we wouldn't need it if we kind of enforce that stuff elsewhere in the CPU, which would be done in the write back stage, which I would kind of want to do actually. And also whenever we do like the hazard detection logic, we would just skip things that write to R0 as well. So there's, yeah, a lot of details kind of swirling around in my head, but mostly a lot of this stuff's pretty simple, except this core, or like the ALU is also really straightforward because we just have these ops. And I don't think I did, but I think I should order these such that they match the bit fields that we could just pull right out of the instruction, so then there wouldn't even be a decoder there. But yeah, the CPU mostly just ties units together, and I think most of the stuff that's in here that's interesting is this core, which again is this big state machine. And it's mostly to do with decoding instructions, and we can also detect misaligned PC errors and a couple of other things. But generally, it's not too terribly difficult. There's an initial PC value, which of course corresponds with my memory map, which is this is where program ROM is, and this whole thing is mirrored here. And then you can see I have some system registers because I have an interface to write to the LEDs on my board. There's 3 of them. And then I have one for the UART transmitter and the DDR memory. So I actually made some decent progress. I think I only worked on this really, really hard for a few weeks, and then kind of fell off of it. And I wish that hadn't happened, but a lot of things happened in my life then that needed more attention. So one of those things. Anyway, I'm excited to get back into this, and I think we should just kind of start. I expect a lot of this will end up kind of copying over, but what I want to do is just kind of focus on each sort of stage in turn. Now, the one thing that's really important that we have to talk about, and I mentioned this briefly, is the way that the main sort of system memory bus works. Because on a lot of these systems, it would be much simpler if like we could put an address on the bus for when the CPU is either going to read or write memory or instructions, which is also reading and writing memory. But it'd be nice if we could put that on a bus and then get the result back the same cycle, because then we wouldn't have to have like a bunch of these wait states. But I'm guessing that we actually need to do that, because when we issue a read, we actually don't know when that data is going to come back, and we have to account for that, and that's actually really annoying. If I wanted to simplify this, one way I would do that for sure is to eliminate the requirement for external DDR, and I would just make it so that you needed to do all the memory on board and just reduce how much memory we have. But I want to use DDR memory so that we can have a full frame buffer eventually. So I just think let's just work around that now anyway. We'll end up with a more robust design regardless. Freefield says, what's the clock speed? At this time, it's running at 150 megahertz, I think. So fairly fast. Of course, we're getting like best case a fourth or a fifth of that because of the not pipelined execution. So in that way, we're kind of, I wanted to go for like a mid to late 90s console. Probably maybe early to mid, because I'm not going to do like texture filtering or anything at first. So yeah, I want to SDRAM would make a lot of sense, because then I guess you can read the memory right away, which is really nice. But yeah, because of that latency, that really kills things. But I think we can design around it, even though I think that's what's causing some issues. So actually a lot of this, I think I call it the memory mapper, but I kind of want to call this like a system bus. Essentially, stuff's gonna try to read from this, and I think this. Yeah, this is kind of where everything's hooked up. And sort of the protocol here is that something wants to read data. So I think something wants to read or write, and so it kind of issues this. So we have, how does this work again? Output ready, address, write data. Yeah, these are all inputs. Yeah, so something would try to write some data or read some data. And then as long as it issues a read request, so it holds this high, and then as long as the ready is high, then it knows that that was issued, and then it's going to sit here and wait until it gets the read data valid signal, which could happen on the next cycle. I don't think it can happen right away, but it could happen on the next cycle. And so that's generally it. You issue the write, and then you might have to wait while issuing that write or read if this ready isn't valid. Which that can happen if, for example, you issue too many reads or writes, or if something else needs to use this bus. So in particular, my original plan was to arbitrate the CPU accesses with whatever the video or audio hardware is doing. Right now, I'm actually going to ignore that, even though I've kind of designed around the fact that that might be the case. But I actually want to do a really simple kind of video and audio hardware initially to start out with that I think will be a little more fun and more motivating to work on. That won't actually use the system bus. But eventually I do want to do that so that we can fit a full frame buffer in memory. Anyway, so we need to account for that whenever we touch this bus, that the bus might not actually be ready. That's important. And then we also need to account for the fact that whenever we issue a read or write, I think writes we can just forget about. But then because they're going to be inherently ordered just the way that I've implemented this bus. But then reads we need to account for the fact that they could be ready the next cycle, but they could also be ready at any time in the future. And whenever they are ready, they're only going to be ready for one cycle, which simplifies a lot of things for the rest of the system. So I don't think that's terribly hard to, or I don't think that's terribly strict. I think that's kind of the right restrictions for this kind of memory bus when you have variable latency. I think this is about as good as you can do for making this simple. But again, we need to design around that. Eventually, too, I also want to do like instruction caches and data caches as well. But we can forget about that for now, which really simplifies things. And that's kind of the name of the game. Make this really predictable. Make this as simple as we can in order to get something that's kind of reliable and predictable without spending an enormous amount of time on it, so that we can kind of stay with the fun stuff. If you're interested in going deeper with a lot of this stuff, I don't know how many other projects are like this, but I guess Mr. Liquid has mentioned a book a couple times that looks pretty good. Yeah, prefetching with prediction, that's another thing that, I mean, it's always nice to have your CPU be Spectre and Meltdown compatible, but, you know, we'll see if that feature actually makes it in. Because another thing that we have to worry about eventually, well, maybe it's up to me, is if we do any kind of interrupts, and also having this like one state at a time will help with that, because then we can just instead of entering the instruction fetch state, we can like do whatever handling we need for the interrupt before just doing that. So that would be easy. All kinds of stuff. But yeah. I guess Linux also needs a memory mapper, and a timer. Are those the things you need? I don't know. I guess those would be extensions. But yeah, I'm just going for like game console kind of thing. So we're only going to have one program on there. We don't need like supervisor versus user modes. Also, the nice thing with RISC-V is that you can choose which kind of subset of the instructions that you, or the instruction sets that you support. So in this case, I just chose to do RE32I, which is the base set, and it's not that big. And then we have compilers that work for that, and any RISC-V compiler can target that specifically. And if we try to do like floating point stuff, it's going to fail. But then I don't need floating point for this. In fact, I've even thought about eventually I might want a vector unit to do some kind of basic SIMD. And when the time comes for that, I might even just start with integer SIMD because I think that's easier to implement. Floating point, at least IEEE 754 is something I would hope to stay away from. I could do my own float format too. But again, I think integer would be enough. And with the right sort of pre-calcing of data, I think we can actually get pretty far with just integer vector instructions. When the time comes. Or if the time comes. Really depends. So yeah, I think that would be fun. And I'd rather solve those kind of difficult problems just in software than in hardware, because that's more where my expertise lies. And this project ultimately is for me to learn how to do this and how a system like this could work. And I think it's fun. But yeah, so if I remember the interface to this, as long as we get a valid ready signal, then we want to issue something. And I think we can also like issue something, and then within that cycle, we'll get if ready was valid or not. So we need to just keep issuing that until we have a cycle where we are issuing it, and then ready is valid, or is high, and then we can stop issuing the read or the write, and then on a read we have to wait until the data comes back. So I guess not that terribly complicated, but for our CPU, our instruction fetch stage and our mem stage both are going to have to care about this. The other stages aren't going to do so much. But I'm thinking that what we're essentially going to have is a hardware unit for each of these, and then, I don't know if this was clear, but we're going to have some kind of control hardware, which is going to, just control all these. Especially like enabling and disabling these different stages, depending on their outputs. And at some point, like if the instruction fetch or decoder, wherever we put that, is waiting for like a read, in fact, it's probably actually going to be the write back and delay ones, or I'm not entirely sure. But if any of them are waiting on a read, they're probably going to have some kind of like stall request line that they're going to give back. But other than that, I think most of this stuff will just fit like this. So these control lines would be probably enable lines. And then what comes back is some kind of not ready or stall request or something. Maybe not ready is a good way to do that. And so then this control logic should just more or less be a state machine, and that should be pretty trivial. I think we're going to end up with a lot of registers in here, maybe not that many, or maybe just like one 32-bit register per one of these, which is going to be the instruction itself. Who knows? But I think overall this would end up being a pretty simple design. I had some stuff like this load and store unit that would try to kind of simplify some of that waiting, but ultimately I think this was not a very good idea. Oh, that was also why I did this. I totally forgot about this. Now I know why I did this. This was to allow misaligned loads and stores in hardware, which you're not actually required to do in RISC-V, if I recall correctly. To be compliant, you don't necessarily need to do that. So I might actually drop that in our hardware. Oh, good find, ArcSecond. Strategies for pipelining. That's actually great. I'll definitely have to read through that later. But yeah, I think for now we'll just ignore that. Revel says, do compilers generate misaligned reads and stores? I don't think they should. I don't know, though. I don't know if that's a software constraint. For example, in my ROM, we're reading characters at this address, at this const char pointer, incremental pointer, and I don't know, because I'm guessing like that would be misaligned load, and in this case, I would detect that and go into an error state. But like we could also rewrite this such that it would be aligned. But then we need the string itself to be aligned. And I'm guessing that the compiler would make sure that that's aligned, and that if you read past this, as long as you're doing an aligned read, that would be okay. And then we could re-implement this in software that would respect the alignment constraint. And maybe that's a good idea, actually. I'm thinking that that's probably smart. But yeah, that is a good point too, that the compiler is free to generate an align, load, and extract what it needs, and then that would enable this to be done with from the compiler, which would actually be good. So I don't know if the compiler does that or not, but I think actually let's do that. I could just get rid of my load and store unit here. I'm actually gonna go on Git here, and I think I don't really have any diffs that are worth anything here, just small changes. So I'm just gonna check out a branch, new CPU. There was actually one more thing I wanted to do with this, which was kind of see how many gates there were, but I think I was about 5,000 logic units, which I think is about 15% of what my FPGA has, and about half of that is the DDR driver, so it's pretty nuts. Yeah, I can definitely use those gates for caches. That's definitely something I'll want to do. But first, we got a lot more hardware to implement. And things like caches, I don't think they would be terribly difficult to implement. But again, we don't have to. And the things that I want to do is I want to do some basic audio and video hardware. So we're just trying to get to that. And I'm excited to get to that. But yeah, let's just start kind of splitting this up. I think I'm just going to delete these loads and store units. And the other thing is I also have this read buffer thing. And I don't know what this was. Just buffering that. I'm not really sure why I needed that, so I'm going to delete it. The register file, I mean, this looks good to me. Except, again, I might do it so that all of our write adders are valid, which would be nice. Yeah, it looks like I have 2 read ports. Or, yeah, that is what that is, 2 read ports. Wonder why I needed that. I don't know. For audio, what I was thinking is I would just have a ring buffer, and you'd be expected to populate that, or keep it populated, because that would be the easiest way to do it. But I might do like some kind of basic synthesizer. I'm really not sure. It's up to me. So those are at least two ideas. Yeah, this is Verilog. This is System Verilog in particular. My curiosity. But I'm gonna do this because I don't know why I had 2 ports. So until we need it again, I'm gonna remove this. Oh, I actually totally know why. It's to do the 2 different arguments for the ALU. So we actually do want that. And then we'll just always have those read from this, which is nice. Yeah, so we'll keep this register file. This is great. And this ALU, I think, is also, I think both of these are almost entirely combinational. This one should totally be that. We have the left-hand side argument, the result, and then we have the shift amount, which is this just the simple decoding, and then all the different things here. So this is actually great. I'm gonna keep this. Yeah, exactly, free fall. I was gonna have a frame buffer, but I think I might do something simpler in the interim because again, for both, for that ring buffer for the audio and also the frame buffer for video, I need both the audio and video units to be able to access the DRAM. And for that, I need to do some arbitration between those and the CPU. And I might just skip that for now. And do something simpler. We'll see. Yeah, totally something tile-based or even something. I'm actually thinking something like Atari 2600, where everything is just registers and it only does some like horizontal stuff, and you're expected to change those registers every scan line. So I'm kind of thinking to do something like that, just to start out with. And the simplest implementation of that is to just do a background color. So that should be pretty nice. And our CPU should be fast enough that racing the beam, yes, that's totally the term, should be okay. We'll see. Anyway, then there's a CPU thing here, which ties this together, and then the core, which was just kind of where a lot of this ended up. I'm guessing the CPU, this top level abstraction, will mostly hold. I mean, these are still the inputs we want. This is our system bus interface, and then we have the clock and the reset. That's going to stay the same. And of course, we have this load unit, store unit, which we're going to get rid of now. Which will hopefully simplify things. The store unit as well, we can get rid of, because again, we really shouldn't need that. I would rather solve those issues in software. I don't know why I decided to put that in hardware before, but I think we'll be happy about taking that out. And then yeah. Not sure what these extra signals were for, but they probably was glue logic to hook this up to the load and the store unit. So let's just get rid of some of this stuff here. Yeah, because the core also interacted with memory and the load unit. That seems strange. Again, most of our core is going away, so maybe I'll just delete all this, actually. It's just moving from the load and the store units. We shouldn't actually have any. I mean, again, this is all combinational. Yeah, we're just going to get rid of this. Yeah, great CPU. Ah, that's what it was, Dark Second. You're absolutely right. I totally forgot about that. Yeah, RISC-V does require traps for software unaligned loads. That's what it does for the unaligned loads. That's exactly what it does. You're totally right. The compiler will generate... it'll just do the loads if they're unaligned, and then it will expect that a trap happens when that happens, when you do an unaligned load, and the trap will then handle it. So what I think I'm going to do is ignore that and see how far we get before we actually do get an unaligned load and store. And if we can work our way around that in software, I want to do that for now. But I guess this redesign of the CPU is also going to make it easier to do exceptions in the meantime, or traps. And so maybe we want to do it that way. Let's try to ignore the issue for now. If nothing else, it'll make the hardware simpler, which is a good design goal here. And then if we end up doing software traps for unaligned loads and stores, which you're totally right, that is what it is. I totally forgot about that. And we'll deal with that. And this core, I think I'm just going to keep around in my directory tree here. But we're essentially going to re-implement most of this. In fact, I'm actually going to pull that down because there's a lot of details about which bits go to where and how we decode instructions and stuff that I don't want to just rewrite because we have it here. But hopefully the overall stuff will be so much simpler that we can just copy that stuff. And then we need to... I'm going to have to go through and change all this stuff, include that in the Quartus project, but we'll deal with that later. Right now we'll just work with the software simulation stuff. And for that, I think the make file here needs this. Yeah, because we have all this stuff. So we don't want this read buffer. Core will also go away because now instead of the core, it'll be separate units and a control unit, which think that makes sense. Store unit goes away. Loan unit goes away. We still have the ALU. Memory mapper, again, I still want to implement that or rename that to system bus. Let's not do that right now, though. Great. And then I think everything on top of this should look the same. The xenowing here, for example, should just be wiring all that up. And our interface, our external interface on the other side of the CPU, that hasn't changed at all. It's still just the system bus interface and then the reset and the clock. So that's perfect. And then, yeah, this looks good to me. Let's do RTL CPU control.sv because we know we're going to have some control logic. So we'll just start with that. And do some boilerplate here. I haven't written system Verilog since I worked on this last time, so I'm going to be real bad at this. But we'll get there. Right, because we have this is going to be our interface, and then our other stuff is the end module. Yeah. And here we're also going to have our input, reset N. And we definitely need our input clock. But yeah, I think we can totally avoid that unaligned load store issue if the software just never does that. And an easy way that we can get around that for now is we can have kind of like an error state that might contain like an error register or an error PC, which will eventually become our trap unit if that's, or trap logic if that's what we want to do. And we can just have that include stuff when we load unaligned stuff. Yeah, I think that makes sense. We'll at least be able to see that easily in some kind of logic analyzer. We can see where it happened and then corroborate that with the ROM, and then, yeah, I think that makes sense. And we can just debug our way out of that. Again, it makes more sense to me to put that complication in the software. So I think that makes sense. Anyway, since we know this is going to be state machine still, so we are going to implement that next. I'm just going to copy some stuff with how we did that. And so it looks like I did something like, we'll worry about the other signals as we have to actually make them. Local param state. It looks like I had this initial instruction fetch setup. That should just be done on reset, I think. I don't know why I did that way. Yeah, thanks for the heads up, Movie 00. I really need to fix that. Whoops. But let's do the state instruction fetch. And I mean, I don't know how many states we're gonna have yet. Right now, this is gonna be a 1-bit state. But we know we'll at least do like state instruction fetch, and then we'll do a state decode execute. I like calling that both. And then we know we're going to do a state mem, and maybe we don't actually need this. So it looks like we're going to have 2 bits here. And it looks like this might work out really well if we end up with 4 states. Of course, I know that if we have some kind of error, that's going to be another state. So maybe we do 3 bits and everything else just goes to error. Not sure. 1 down to 0 for 2 bits. Yeah, that's a good point, Dark Second. Good to have that flag. Kretzev, definitely. That's great. Fashionable. Okay, so then let's do some reset stuff here. Now, one of the things that I was doing when I implemented this last time is I used this this sort of, what is it called, two process style. I think let's keep using that. It's a bit verbose, but it makes things simple for me to understand at least. And whether or not this is a good idea, honestly, that's a discussion for another time. But we're gonna do it this way. So state next is state. Yeah, I think this style is at least very accessible for software guys like me. And that's good enough for me. So if it's reset, then we want to do state is state instruction fetch. Nice and easy. And then otherwise this, and this will be state is state next. Great. So we want to do this here. These parallel stores for, is that what they're called? Parallel assignment? I think that's what it is in Verilog. And then these sequential assignments in the combinational block. And so far, that's it. That's all we do. Great. So we're on our way. The next thing we want to do is our instruction fetch unit. And I'm going to do this as instruction fetch.sv. And we're just going to add that to our makefile. And the other thing I want to do is we need to instantiate this. What did my instantiations look like in the other one? They looked like something like this. Also, the register file right now was instantiated in core, and I'm totally going to move that instantiation out to this CPU because that makes the most sense. Yeah, you're right. That's exactly it, Mr. Liquid. Non-blocking and blocking assignments. You're absolutely right. That's what it's called. Glad I have you guys. Very helpful to get back into this stuff. Yeah, that's what I was doing. We want to instantiate the control. So we're going to do control 0. And I think right now this just had clock and the reset. Good. I'm glad, Dark Second. Yeah, I've missed doing them. For sure. I've also missed this project in particular. Thought a lot about it in the last year. So it's nice to play with this again. I think also there's going to be some like more architectural state, like the cycle register, the instructions retired register, and that's probably also going to live, either be instantiated out here and live in the control or live in the control unit. Kind of makes sense for that to be in the control unit, right? Because it's the one that's going to know when those transition at least anyway. So that makes sense to me, I think. Hey, Skeleton. Yeah, it's been a while. Yeah, I'll also instantiate the ALU here because we know we're going to have that. Actually, you know what? I'm not gonna, because the execution stage might instantiate that. I don't think anything else is going to use it. So if we're not doing any kind of glue logic, then I'd rather have it instantiated there. Yeah, looking good. Register files should be here, though. Did I already say that? I think I did. Oh yeah, but I wanted to wait until we actually get some signals that use that. Let's do that. Let's wait. So we know what to hook it up with. Good. No, I haven't, Skeleton, but I think Mr. Liquid mentioned that earlier. But I bet it's cool. Or someone else? I don't know. I feel like someone mentioned that earlier today, and I just caught it. Saja Attack or Sai Attack. Yeah, he mentioned it. Sounds like I need to check that out. That's Glad Movie 00. I think it's cool to see. I mean, it's similar content in the sense that we're understanding how systems work, but we're doing it in a very different way. Oh, that sounds awesome, Skeleton. Yeah, definitely gotta check that out. But yeah, let's do the instruction fetch unit. So the instruction fetch, I'm actually going to copy this because we're going to have a lot of these things hooked up, I think. So yeah, particularly we need the mem ready. We need mem adder. We're not going to be writing any data. We do need byte enable. We need read request. We need read data and read data valid. We're going to need all of this to operate properly. Now, I think those are kind of the signals we need. We will also have our own other signals. So I think what we're going to do is maybe I'll put this here because this kind of makes sense. Input enable. And then I'm never sure how to order a lot of these different parts of the interface, but I think enable makes sense because we need clock and reset. We need whether or not we're going to be running effectively. And then I think we also need an output for, I guess we can call this ready. I kind of wanted to call this like stall request, but I think ready makes sense because we use that in other parts of the design. I think that makes some sense. Because, for example, the instruction fetch is only ready when it hasn't issued data, but when this does actually issue a read and it's waiting for it to come back, it's not going to be ready until it comes back. So I think what we want to do from the control is drive enable high and then essentially keep doing that until we have a cycle where enable is high and ready was low. Or ready was high as well. Is that how we want to do that? Might have to think about that one. I think that is what we want though, because we'll do, if enable's high, we'll drive ready with some combinational logic. So within that cycle, we'll essentially drive it. Enable will come high and then ready will go low probably as we issue the read. And then whenever the read comes back, then we'll have a cycle where it goes high and then we'll transition into another state internally here. Because in this case, we're going to have both that sort of issue and the wait state here. Again, this is why I thought about splitting that up, because we can always like drive the enable to just issue the read, and then we would have a separate unit for when that read comes back, which is kind of a design that I like. Aaron was confused by so this is the interface, and so this here ends the interface. That's part of the module declaration. And then stuff in here is where our logic is going to go. So yes, this is the interface, and then this is the module and the end of the module. Should clarify that. Effectively, what I've made here is an instruction fetch. This is kind of like a class, or like this is what like a definition for a hardware unit, and so this has the input and output signals coming in and out of that box, and then there would be the logic inside that box here, and then if we instantiated this, which would actually dedicate some hardware to implementing that, then that's what That's what this is doing. For example, this is an instantiation of the control box. And we're going to have another one for instruction fetch, which will look something like instruction fetch. And then I've just been calling it something like 0. And then this will also wire up clock to clock. So this is saying the clock of this unit in that interface is mapped to this value. And we'll do the same for reset. And I kind of hate how this, how there's all this alignment crap in here, because I don't like that. But yeah, to do that, I know there's going to be more stuff there. So yeah, that's kind of the basic syntax, and then there's some other stuff that I don't want to explain right now. But yeah, at least that's kind of high level of what this looks like. But I think actually I do want to go ahead and make this have different states for issuing the instruction fetch and then waiting for it to come back. So we have an instruction fetch issue and an instruction fetch wait unit. And then the control logic is going to decide which works for those. And then we still need a ready signal, because it's possible that when we're trying to issue the read that we can't do that if something else is using the bus. Remember, we're trying to design around that. And that's also why splitting this up into multiple stages, it might seem like it's more complicated, but then each stage gets simpler, and that's what I'm after in particular. So then we'll have an instruction fetch issue state, and then we'll also have an instruction fetch wait state. And now, of course, we need more bits for the state. And we also want to start an instruction fetch issue. Also, the instruction fetch unit is where the program counter is going to live. And it's going to also do the increment for that. And again, that's going to set us up better for pipelining in the future, even though right now we're not going to implement that properly. I also do want to have an error state. Which might become our trap state later. We'll see. Yeah, I like this. So then we'll go back to our make file as well. It's really dumb that you have to, with Verilog, specify lists of files like this, but this is what we're doing. I know I'm going to have an instruction fetch wait. That's why this is here. But the nice thing about this is that this gets simpler, because this just does if the memory's ready and then the address and the byte enable and the read request. We don't have the read data or the read data valid parts of this interface that this unit cares about, which I think is nice. So I think we're going to want registered outputs for this that we need to do. Yeah, because this is the actual bus. And again, I should also call these like bus addresses, but it's because it's a mem mapper that they're prefixed like this. You know what? I'm actually just going to do that. I'm going to rename this. I'm going to call this a system bus. And there's probably going to be a lot of things that we want to rename. So here it's just called all ready and that kind of stuff, which makes more sense. There's our system bus, and also in our make file we need to change that. And this is part of the system bus is doing memory mapping. I think that makes sense. In our docs as well, I have this written down. Whoops. Xenowing. Doc. This here. It's kind of cool because I think I have in my make file, if I just make all, or I think make docs does it, and then we have the memory topology doc regenerated, which I think ends up looking like this, which is nice. So yeah, the system bus now connects all of these, which I like. This probably would have been a good thing to show earlier. Sort of the overall system architecture. System bus obviously connects the CPU to the rest, program ROM LED interface, the UART transmitter, GPU display and GPU draw, which I wanted to have as separate units. So the display is the one that's going to sit here and just pull pixels out of this at the right times. And then also this would be hooked up to the HDMI transmitter. And then the draw unit is going to be the thing that we would somehow issue commands to. And I think I wanted to do that by preparing a command list in memory and then pointing the GPU at that. And then it would go and read those commands and also write back pixels into the memory. So you'd get a pipeline through here. And then there's this whole thing about like what takes precedence, the CPU fetching instructions or the GPU drawing or the GPU displaying. And then you have all this arbitration, which is why I have this DDR3 arbiter. But I don't know if this arbiter ended up being a separate unit or not. This might be out of date because I think I might have ended up doing all that through the system bus. I don't really remember. So maybe we'll have to go through and change that, but we'll get there. Maybe I just didn't even do any of that yet. Hey, Molif. But yeah. So I need to change that in a couple more places. Particularly the xenowing itself. Yeah, this is the one that connects this, what's called the Avalon interface, and that's what we get from the generated DDR3 core, and hooks that up to the memory mapper. And then the mem mapper, this is just what we want to rename everywhere. It's hooked up to the CPU and this Avalon stuff, I think. Or maybe the memory mapper actually contained stuff for the DDR3 interface. That's what that was. Yeah, anyway, this is going to be called system bus. And then the CPU instead of mem, whatever. Just call this the system bus because we know that's what it's interacting with. I like that. And then if we have caches, we'll instantiate them here because that's still part of the CPU. That makes the most sense. This all lines up nicely in my head. So the instruction fetch, we also know that we're going to need these, which we're also going to call system bus. And what I like to do is just copy this here. Just delete all this other crap that this part doesn't need. And then we want to just do that essentially. A lot of this code ends up just being what do we connect what to what, but so does hardware design. So that kind of matches. Yeah, Dark Second, I have a lot of issues with that as well, which is why I've done so much to be able to work without it. And also, of course, the iteration times are quite bad. Oh yeah, we can't actually make this because the instruction fetch wait we haven't done yet. Let's go ahead and actually kind of instantiate that now. Wait unit, and of course this is going to have a different interface. In particular, I'm going to copy this again. And this doesn't actually need bus ready, or the bus address, or the write data, or the byte enable, or read or write request. It just needs these two read data and read data valid signals. Cool. So then in the CPU, we'll instantiate that also. Also, this instead of instruction fetch issue. The CPU has issues. And then this will be instruction fetch wait. And again, we just need these two. So far, we will also need some control signals, which we will get from our control unit, which we'll hook up as well. And so a lot of what you'll see here too is if we look at, for example, the xenowing top level thing here, there's a lot of these logic signals here, which is literally just me giving names to signals here that we can hook up to signals here. And that way we can hook these signals up here to these and then hook these up to these other things. So these are essentially just big wires or buses, these here, that we connect on one side to this, which in this case is an output of this unit. And then when we hook it up to this is an input to this unit. Also, this mem whatever needs to all be system bus, which is nice because then they also align here. So looking really good. Well, yeah, it would be nice to have like a shorthand for that, but you need to know. I mean, it might be possible to say like ready for this is the whatever the other name of that instantiation dot whatever, but yeah. Sometimes it's nice to call these different names in different contexts. Like in this case, the system bus here. It's just nicer within the system bus to call these for these names, where out here we want to prefix it with system bus. But again, I guess you could do system bus 0.ready. And maybe you can hook it up that way. I don't know. Maybe that's a better pattern. This is the one I've gone with so far. Bit verbose, perhaps. Yeah, it would be nice to just take whatever the thing is of the same name. That's true. That would be nice to have that kind of shorthand. Anyway. So we definitely know that there's going to be some other outputs here. So output, instruction, fetch, issue, enable, because we know where we want to drive that. And then we also know that we need to have an input here. Instruction, fetch, issue, ready. And I think I might reorder these. Fetch, wait, ready, and I would think that would be likely def param if it has that, and I just wouldn't know it. This should be output, by the way. So we're going to want to drive these. And then our CPU obviously needs to hook these up. So we're going to have something like logic, instruction, fetch, issue. I actually want to reorder these to have the control at the bottom. Instruction, fetch, issue, ready, and logic, instruction, fetch, issue, enable. And maybe enable is not the right one. Maybe select is a better word. I'm not entirely sure. We can always change this. Implicit wildcard connections. Oh, controversial shortcut. Yeah, I'll read that in a bit. But I'm guessing that's a nice shorthand. So then this one will do, of course, ready will connect to instruction, fetch, issue, ready. And then enable would be instruction, fetch, issue, enable. So we sort of fan out these signals here, and then we also want to hook those up to the control here, which will do this. Yeah, that's a good point too. System or Verilator might not support that. I mean, who knows? The way to check is to try it, but I'm not gonna just because I've already used this pattern here. Maybe later we'll check that out. Anyway, that looks good, and then our instruction fetch wait is also going to need those hooked up. Did I do that in the control already? Yeah, I did. Good. Whoops, I put this in the wrong place, didn't I? I already had these here. For ready enable here, let's do dot ready. And then here we'll do hook these up as well. At DevPram, your new job is more hardware-oriented, involved with FPGAs. I'm not directly, but there is an FPGA team. I work at the rack scale team for a company called GraphCore. So we're making big computer brains, or big artificial intelligence brains. If you go to graphcore.ai, you can check out more. I'm very happy to be there. So a couple things here that I need to see what my pattern was previously. But if we have like this store unit byte enable. Oh yeah, this is actually really nice. Here in the control, we want to make this registered. So I'm going to put logic here for these outputs. Then we're going to have next values for that as well. So the state, and I think we also want to do, I think I like to try and keep all these kind of in the same order. Simpalaxy, thanks for the follow. So we need some next signals for this. Yeah, it looks like that's exactly how I organize this. So we'll do logic instruction, fetch, issue, enable next, and logic instruction, fetch, wait, enable next. And actually, we might not even need these to be registered. If we just do it based on the state. So we might also want to change that actually. I don't know that project, Simpalaxy, so might be similar, but definitely not related. So yeah, I'm going to actually instead just drive these combinationally. So I'm going to say assign instruction fetch issue enable is going to be state equals this. And assign instruction fetch wait enable is going to be this as well. And I like when it gets that simple. That's a good sign. If most of our code is just simple routing like this. Yeah. And this is safe because this is registered, so this will look good. The ready stuff we might need to do though. I need to worry about, but I think that's actually just the transitions. So then we don't even need initial values for these registers, which is nice. And then here, we'll do the state transitions. He had a series of the same name? That's funny. Right. So initially what we want to do is we want to enable the instruction fetch issue unit. But first, let's actually just look at that, what this is going to look like. So I think... we want these to be registered. And so we'll do some boilerplate stuff here. And actually, some of these we don't need to be registered. I should actually wait on some of this, shouldn't I? Because, in fact, this might end up being entirely combinational now that I think about it, which is going to be nice. Mala wants to get into FPGA design. What do I do? I'm not the guy to ask, but some guys in the chat probably are. Find a project, buy a board. Those are good places to start. So I want to, well, I know I'm going to have a program counter. So we'll set this up. Whoa. No. So I think I had the initial PC was just this. And that's the style that I've been using here. Good. Philadelphia, that's basically exactly what it is. So you're essentially designing logic circuits. And then the hardware becomes that. It has a configure step where it kind of configures all that, and then it will emulate what you've designed here. Hey, Pyro. Good to see you again. Yeah, you don't need to. That's true. You totally don't need to actually buy a board. You can do a lot of stuff with software simulation. Very true. Okay, so there's our program counter. Not very exciting, obviously, but it will be. So we need to do some stuff here. Essentially what's going to happen is the control logic is going to enable this stage. And when the stage is enabled, our whole purpose in life is to put out the program counter onto the system bus address. And of course, all the byte enables. And in fact, I can assign this to a constant, can't I? Because we know all these are going to be true in this case. So I should actually be able to do just an assignment here. This, so we just always have all the bytes enabled because we're only going to be issuing words, and that should be done with the PC. Seems like it makes sense. So yeah, so the system bus address also is just going to be assigned to the program counter. In fact, I'm going to move my assigns down here. Like that. Great. And this is an input, and then the read request. That's what we need. So a couple things here. We need to assert the read requests as long as we're enabled, and as long as the system bus is ready. That's kind of what we're doing. I didn't realize this series is called Risky Business. That makes more sense that it was under the same name. Now that's just like the name of my episode, because we're going for more risk-like, more pure risk-like design here. But yeah. So again, the interface here, it should be relatively simple. We're getting enable from the control logic, and this from this. So we need to do the right combination of this so that on the next, whenever this gets asserted on a cycle that this is asserted, we basically want the control logic to assert the next one only if ready is high. So we want to assign ready to probably system bus ready. But I think that's actually it for the issue. Maybe that's all we do, which is nice. In that case, it's assign system, or assign ready is system bus ready. Yeah, Pyro, actually one thing that can help is if you do like this sort of 2-process style, then within your one unit, this code kind of acts pretty sequential. It's still happening. You can kind of think of this sequential program will sort of run every cycle. And there's some limitations to that, but then your whole interface is like, what are my inputs this cycle and what are my outputs next cycle, which is kind of nice. Yeah, exactly, Philadelphia. That's absolutely true. Yeah, another series called Ferris Makes Harder would be funny. And unlikely, I hope. Okay, so what we want to do is essentially if ready, oops, not braces, begin and then end. And here what we want to do is PC next is actually if enable and ready, then PC next is going to be PC plus 4. So essentially, if we're enabled and we're able to do the issue, then we're going to do PC, then we're going to increment the program counter as well. That makes some sense. Eventually, too, we need to support branches and jumps, and that's going to be some kind of input as well, which is going to override this. And so how I'll probably do that, and then it'll be something like if PC override valid. So we'll have a signal for the valid, and then we'll have another signal for the data, and then we'll do PC next is PC override data. I think this should be called data valid, because that's typically what this is called. We have a data valid and data. But we'll get to that. In fact, for now, I won't do that because we don't have any unit that actually needs that, so we're just going to leave that out. But then I think this is it. I think this makes sense. So we're going to get an input signal that is we're enabled. And if we're enabled and ready, then we have done our job, and then the PC on the next cycle is going to be the incremented one. And essentially the control logic is going to drive enable high, and then while, and then on the next cycle, if ready is high, while it's still driving that, then it can transition to the next state. Otherwise, it's going to keep driving enable high until it ends up being that when it drives enable high, ready is also high, and then we should be good. And that should just be a matter of propagating the system bus signal. This was a lot more complicated when when we were trying to also do unaligned stuff, because then I think that's totally why this is complicated, because then if we wanted to do an unaligned read, we actually had to read 2 words and then return the data from within that. So this should make the design a lot simpler, as we can see by how simple this is. This is a single register in the instruction fetch unit, which is pretty great. And so then control, we want to do the logic that matches that in the control unit right now. So let's do this. We need a case thing here. Maybe Colomos, but I don't think it would be nearly as fast. So do the state. I think end case is how you do that. And then we're going to do state instruction fetch issue begin, and then we should have end here as well. For RISC-V, the instructions are required to be aligned, I think. Yeah, DevPrep works at Intel, by the way. I forgot about that. That's great. We're also going to have this state. I'm only going to do the states that we know of. I'm also going to, just so that we're safe, I'm going to have a default here. Just to catch that. So I don't know how that would ever happen because of this, but just in case, then we're always decoding something. Although actually just having this feedback would be okay too, but yeah, actually that keeps the logic simpler, and this should never happen. Let's go with that. Okay. Yeah, it is Pyro. I'm remaking the CPU. Gonna try to make it simpler. Exactly what it is. I still want to use RISC-V because I still want to have the whole software stack. Again, I think we could design a CPU that's a lot simpler and then just make the software part more complicated, but I think this should be a good balance. Oh yeah, that's cool, DevParam. Yeah, that should never happen. Famous last words. Okay, but so this state here, the nice thing about this is that for the states we don't cover, if it transitions into those states, it'll just stay there, and we'll catch that in the trace for the simulation, which is what should happen. So essentially what we're going to do is, yeah, so this will be enabled as long as the state is this. And so I think this ends up being, yeah, we're in this state, so we know that we're doing this enable line, and then it should be a matter of if instruction fetch issue ready. Then state next is the wait state. I feel it's generating the control signals for all the different pipeline stages, not just the ALU. I drew this really nasty diagram that shows sort of the different pipeline stages that exist, and the control is kind of controlling which time each one is active. In a proper pipeline implementation, this would drive these at the same time and might have to do some like stalls and stuff like that. But for simplicity, I'm just going to do a state machine that just does one at a time. This will be slower, but it should be simpler. There we go. So with this, we have enough to test something, I think. So we're probably going to have some errors here. Multiple top-level modules, ALU and xenowing. I wonder if it thought it was top-level just because I didn't instantiate the ALU anywhere. That's might be what happened. In that case, we'll just remove the ALU from this because we're not using it right now anyway. Very later output. is not very friendly, by the way. Could be a lot worse, but it's not that friendly. And the register file will also get rid of. We got a bunch of warnings about unused stuff. Some stuff being undriven. I'm actually okay with that. Cool. But yeah, this actually did work because it ran my simulator here, and then we just get a trace. So what we want to do is we want to go ahead and look at this. Gonna pull up GTK wave again, and we're gonna open up the trace. And essentially what we should see, exactly skeleton. What we should see, if we look at the top here and the xenowing and the CPU, we should see a couple nice things. I want to add the control logic here, and I want to add the state. And then I want to look at the instruction fetch issue stuff. And yeah, actually all I want to see is the state right now, except I do want to see the PC, which we should see here. So if we zoom in, there's going to be a bunch of time where essentially nothing has happened. And what that is this happens while there's some initialization. I think the initialization is initializing the, or I think this is reset in the simulation, which should make sense. Because reset, these are whatever value, and then after reset, this value is going to be latched, so that makes sense. And then I think this is just some simulated time for the memory to initialize. On the actual hardware, this can actually be quite a long time. But in the simulator, in my simulation, I think that's pretty short, just to keep the length of these traces fairly manageable. But then at some point here, we should actually see, if we look at the system bus stuff, I'm going to append all this stuff here. In fact, we'll do... We can look at all these system bus lines and append those. And if we look here, we should see a few different things. First of all, the byte enables F, because we're always going to read those. The read data, it might have just read 0, which seems strange to me. But we put this on the system bus, because that's our PC. And at some point, this incremented. So at some point, the system bus ready was valid, which is what we see here. I think, actually, let's look at the reset and append that as well, and then we can append the clock. This might actually be happening a lot faster than I realized, and it looks like it is. Yeah, so here you can see we have a cycle where the reset happens, and then we come out of reset. And at some point, looks like the system bus ready is always on, which probably makes sense because we're probably able to issue that read pretty quick. And I think what I have actually is that the reset line is actually hooked up to the memory initialization. I think that's how I did it for most of this logic, which is fair enough, because we can't really start the system without that being ready, and that just makes it easy. So yeah, I think this actually makes sense. Here we have a cycle here where, we come out of reset and then we get a clock. And when that happens, well, our system bus was ready, which is here. And so then it says read data valid and read request, which I would have expected. Read request should have gone high, shouldn't it have? Maybe we're not driving that. Yes, we're totally not. That makes sense, actually, because we need to make sure we actually issue this. This is a good thing that we're looking at the trace. So for this also, I think this is just this. System bus read request is enable. I think that's all we're doing. So we'll run this again. I'm going to compile, and then it ran the simulation. And this should reload the same file. And here, now we're looking good. Because now we see we got some read data here. So here we issued that we wanted... yeah, okay, so here's our cycle, actually, where we've come out of reset. Or should be this edge here. Come out of reset. We've said that the read data valid is, yeah, because we're issuing a read request on this cycle here. And we should have done that read request with this PC. So this is already wrong. I don't know why that is yet. So we'll have to look at that. But essentially, we're issuing that read request, and then we can see the system bus actually says it's not ready after that. And then, does that ever come back with something, or what's happening there? Yeah, it's a bit less code than I expected too, Dark Second, which I think is a good sign. But you know what? I actually think... I'm actually not sure about this. This seems wrong to me. I expect that this is about the amount of code that we need, but I don't think this looks right, because we should have... Actually, wait, we do have the read request high. No, that should have happened at this cycle, shouldn't it have? Yeah. I don't think I'm correct here. Because what I think I expect to see is that on one of these low to high transitions, then this... So I'm not saying anything. I'm just kind of trying to think through this, because what's interesting here is that we do, if we look at this like sort of cycle here, or this half cycle, because this is a whole cycle, we do actually assert a valid PC, and we do assert a read request. And then what happens is we actually get some data back. And if we look at this data, 004006F, if we go in our ROM and we do an OBJ dump again, oh, oops, I did that from this one. We should actually see this, which is the start of our text section. So it did actually read the right data too. No, Dark Second, no way. We do get the right data back, and then that says it's valid, and then we can see that happens on the rising edge of this, and then on the next rising edge it looks good. So maybe this is actually correct. It just seems wrong to me, but maybe that's just a result of we come out of reset, and then this is asserting that already within this cycle. And so then we've already asserted that for this cycle. And then on the next cycle, we can see that our program counter is incremented and we get the data back. So maybe this logic is actually correct. When I'm looking at this, this actually looks pretty good. And then I think the weirdness with the reset and the clock here is just the fact that I do make sure I have a low to high transition while reset is low, and then later I have a low to high transition while reset is high for the simulator. Because I'm actually thinking that this is correct. Because again, for this cycle, we do have a cycle here where we are asserting that we want a read request with our program counter and all the bytes, and then what we get is these 4 bytes back, which is great. So I actually think this is correct, which is awesome. So I'm very happy right now with with the choice to simplify this hardware design. I think, again, the thing that's actually going to simplify it most, other than splitting it up like this so we can look at each unit individually, is going to be the fact that we're not supporting align, loads, or stores, and then having a trap for that's probably going to be a lot easier. But yeah, I think that's our instruction fetch issue. So I want to look at instruction fetch wait, and then I probably won't stream for too much longer. It's getting a bit warm. But I'm very happy with this as sort of a comeback stream. And then we'll definitely hit this next week. I may work on some of these stages in the meantime, but maybe not because I got a lot of plans. Family stuff this weekend. So we'll see. But we'll definitely hit this next week. I'm very, very pleased with how short this turned out, but that's, I guess, to be expected. So then the next one, there's actually another signal I want to put in here, which is in the control. I want to see these lines, these enable and ready lines here. And what we can see here is instruction fetch issue enable. We can see this is high during this cycle here. And the ready is also high. We can see that. And then we also see the wait state enable goes high here. So then this actually is definitely correct, because then when the wait state goes high, you could see we get the memory back. And again, on the hardware, this may not happen right away. But I think in my simulator, I decided to just go ahead and return it on the same one to make it simpler. Or make it faster, actually. So we run less cycles when we're doing useful tests. But yeah, this looks good. So then in the next state where the control logic is driving our wait state, and that's just going to go forever because we don't have any logic to take it out of that state. So let's do that next. We'll do the wait state. And I'm going to pull this out of frame, unfortunately for you guys. But this is going to make it a lot easier for me with this big, stupid font. Now, I think a lot of this is going to be mostly the same as well. Except we do want some kind of output for what the instruction is. So we're going to have another output here. And it's going to be 31 down to 0 instruction. And I actually don't want this to be registered because I think that if we want to insert a bunch of registers between the different stages, we'll do that ourselves as part of the CPU. And then we'll try to keep our individual stages as combinational as possible. Because then the simple implementation here will just wire the outputs of one stage to the inputs on the next, and the control logic will just make sure that it's doing stuff whenever they need to, and then we don't have to register any of this, which is kind of cool. We might want to register the instructions, so we'll actually see that, but yeah, we'll get there. Anyway, this will do. I think this ends up being simple too, because we'll do assign ready is system bus read data valid. And wow, okay. Is the system bus read data. That can't be it. But I think it actually is. And so then the control logic for this state is going to be instruction fetch wait begin. Issue wait And we need the next instruction state, which is going to be execute. What up? Too easy, right? Of course, we're not actually reading that instruction anywhere. I do want to pull that out into the CPU. Fetch wait instruction. That's the output of the wait. Build that and run that. And we should see some more stuff happen on this cycle. So then what happens is I want to add a couple things here. Yeah, do I have a state, by the way? Did I have that here? Yeah, let's have that. Good. So now we see in this first cycle, we end up issuing the read. And it already comes back in the next cycle, which is really nice. And so then we already transition to the next state. And we end up losing this data because we're not actually putting it anywhere. So if the next state needs that registered, we're going to want to actually register that. But so far, this is looking really good. That's great, Mr. Liquid. Yeah, I wouldn't recommend necessarily watching all of them, to be honest. I mean, I should say that, right? But like, we did a couple with formal verification where I just kind of struggled to set up some software stuff, but it's interesting to know what that stuff is, I guess. But the other stuff was really fun because I streamed for like 8 hours the first day or something where I gave like an introduction to the project and we started doing the CPU initially. And there's a lot of stuff on risc-v instruction decoding, which I think is going to end up being so straightforward. Or at least that we can copy and paste a lot of it, where I won't go as deep into it probably. Thanks for the sub, Dark Second. I really appreciate it. But yeah, I'm liking this design so far. I mean, obviously we've done some of the easier parts, but still, I'm liking this design so far. So one of the next things that we want to do, I mean, why don't we just go for the next stage already? I think the next one is where things actually start to get somewhat complicated because we need to do some stuff. In fact, I actually know that's great, Dark Second. I'm glad. I'm still honored you used it on me. I really appreciate that. of all the streams. I'm just kind of thinking again with the execute stage. In fact, I might have even... I'm just looking at this other code that I have, and I have like the ALU computing like less than and greater than and all that stuff. I guess we do want that, don't we? Yeah, we do. I do end up using all those, don't I? That's good. And I think I did also order these in the same way that they're ordered. No, I didn't quite order them the same way that they're ordered in the instruction. Basically, the instruction is the 3-bit function field, and those 3 bits obviously pick one of these. 2, 3, 4, 5, 6, 7, 8. There's more than 8 here, so we actually want to reorder some of those. Maybe this doesn't make sense because I think we need some decoder anyway. I'll undo this. Because it looks like... Are there 16 of those different ALU things? There's 14 of them. Yeah, that decoder logic's probably not going to be that complicated anyway, but in any case. We do actually want to have a register between these, but let's just ignore that for now and start working on the next state. So I'll copy this one just to be lazy. Nice, Okama. Exactly, Mr. Liquid. That's so great. So this is probably going to be like the difficult instruction. Sort of decode and execute. And I think doing this right, starting this is a fine idea, but we'll definitely not finish this today. Yeah, I just called it decode execute, didn't I? Then we'll just call this decode execute.sv. Maybe we'll change this to execute after a while. Not entirely sure. Execute. So let's just have this here. Because we know we want the instruction as the input and then something as the output. Whatever that's going to end up being. Dark Second says, why are you combining decode and execute? Because risc-v is so simple to decode, and when you need to load your register somewhere, isn't that what decode traditionally does? I think we can actually... That's a good point, that's probably is what decode does, isn't it? Maybe we'll want to split that up, actually. Where we have one that just takes the instruction and then goes and reads the register file for the inputs. Or it does zeros for register 0, because I decided not to make that part of the register file. And then execute can just take in those inputs as well as some fields from the instruction. Maybe that's what we'll do. And maybe that's a better idea anyway, because that we can finish that tonight, which would be nice. I'm gonna do that. We're gonna get even riskier. So let's go ahead and do that then. And go to our make file and fix that. That's a good point that we're going to want to read those registers. And our register file should be, yeah, we'll put the inputs in it in this cycle, then we'll get the outputs on the next cycle. So this should be correct. And then this will give us a nice excuse to hook up our register file as well, which is nice. So yeah, in the control, we want to do this state decode, and then we'll do another state for execute. We're probably also going to have a mem wait state. We'll do the same pattern here. We do mem issue and mem wait. And look at this. Look at us having exactly as many states as bits. That's exactly 2 curves. Yeah, we're definitely classic risking it up now. I think in the other one I realized that I could actually fold those together if the instruction fetch wait state also would read the registers. But I think it's better that we just do it the nice classic way for simplicity, among other things. So in this case, then we need an input for. Actually, we may not even need a ready signal from this stage. So we'll just do output. Decode enable. And then we can do this. Assign instruction. No, keep doing that because I see the other ones. Decode enable is state instruction state decode. And then we'll do this too. This also becomes just decode here. If we're in the decode state, we're going to begin. And it should just be state next is state execute. Oh, I'm definitely not printing this into Silicon. Just having fun. Running it on FPGA, of course. But yeah. Eventually, I would like to design a board that would have an FPGA on it that would run this, or that would have this hardware embedded in it. So that's probably as far as I'll take it. But we'll see. Might even be a couple years before I do that at this pace. But yes, there's our control for our decode enable, and then we have our decode unit. So our CPU, we want to instantiate the decode unit. We're gonna have this, and we're gonna have the instruction as well. And this we're probably actually gonna want a register here, which we'll get to. Or it might even be enough that just because we know that this asserts this for this cycle, that on the next cycle we have that data. But I'm not sure because we didn't register the output of this. So that's typically what that register would do, is carry that data in the next cycle. So probably have to make a thing there. Anyway, enable will be decode enable, which we are fanning out to signal here. And then we'll plug that in here. And I kind of want, if we have a register that goes between these, we could actually have that as a separate unit too, but it's going to be such a simple register that I think I want to instantiate them at this level. Unfortunately, not 2 curbs. But I am thinking of just storing hydrofluoric acid in my house. Seems like a good idea. Maybe I'll put it on top of my fridge, like G. Superland. Or Polynomial, as you guys might know him. Yeah, exactly, all comma. So this has no other inputs currently. I'm going to do this logic. Or how do we want to do this? Maybe I'll make the register here. So here, I could give this a really long name. Instruction fetch, wait, and decode. Instruction. And then we would have the same thing. Next, to follow suit here. And then we actually want this here. And we want to assign this instruction. No. We could also just put this here. Always comb begin. And then we'll do this is actually this one. And so we can make this simpler, can't we? Because we can do this. Always ff at pause edge clock. I think is the way we write that. And this is just that this here is next, and we don't even need to reset this because we don't really care what the reset state is. And in that case, we might as well, like, we don't even need this pattern really. And in that case, I'm kind of breaking a convention here, but at the same time, this is making a lot of sense to me. So this way we kind of have that register in between those two, hooking it up like that. I don't know, this makes a lot of sense to me. Cool. And so then the decode can have that instruction on its input. And of course, this is going to have to output a bunch of stuff, but we're going to do most of that. In fact, I'm going to run this. Just because I want to see that register behave like we expect. So now we see this additional state transition here, and we can look at our decode, and we'll do our, actually we'll look at the control logic, because that was what was doing, or was the CPU that was doing instruction fetch, whatever. So now we want decode enable. There is no ready because it's always ready. And then the other thing we want to do is this instruction fetch wait and decode instruction, this register between them, which we should see exactly this. This is exactly what we should see, that this register has its value the next cycle, because this one has it on its output, so then it'll be latched for this one's input on the next one. So if we go ahead and look at our control, actually our decode, the instruction here should match that, which is great because now we have it active on this cycle, which is exactly what we should see. So this becomes very natural to write, probably because it's natural to express in hardware, which was kind of the intent of this whole RISC design. So this is looking really good. That'd actually be an awesome compo dark second. Not a very fast one though, but you know, I guess if we had the right inputs and outputs, then it could be fun. But this looks really good. And I'm thinking that this might be all I want to do for today. Except I'm going to do one more thing, and that's I'm actually going to compile it for the hardware. So we need to go and shift around a bunch of stuff in the Quartus project. But let's do that because I want to see, or rather, so what I actually want to see is I don't want to synthesize it and run it on the device because I don't really care. Like, we're not really going to see anything useful anyway unless we do some like logic tap stuff, and I don't care to do that right now. But what I'm thinking is that we can see the output of the synthesis, so we can see what the compiled logic looks like as sort of a schematic view. And I like to look at that after I've been working on this. It's fun for me to see. So this is a good time to do that, I think. And then we'll commit and call it a day. And I mean, we should see very basic stuff. I don't expect this to be surprising at all, which is good. And again, that's one of the reasons I'm doing this. I'm trying to make this simpler so that we can feel a bit more confident about it. So I think what I have to do is in files, we have to move some stuff because the CPU, we don't want the ALU anymore. Remove that file. The load unit has gone away. The store unit has gone away. We're not using the register file right now. Read buffer has gone away. And we should still have the CPU, and the core goes away. And then we need to add another file. We need to add a few, actually, which are in my CPU directory. I don't know if I can, I don't remember if I can add a bunch at once or not. But I need, we want the control, we want the decode, instruction fetch issue, and instruction fetch wait. I want to add all those. Go ahead and apply that. Okay. Now I'm gonna just start the compilation here. We might get some errors, probably get some errors, especially about signals not being driven. But we don't care about that right now because we're just looking at the logic that we should see, or that we have here, which I'm very confident in because of how simple this stuff is. And this will of course take a bit, but I'm also, just to sort of recap a little bit here, I'm very pleased with how much simpler I think this overall design ends up being, where we have the individual units like this, and then of course each of those are basically trivial, at least as trivial as they can be. And then we have these explicit registers in between the basically purely combinational stages. I think that makes sense. The only ones that aren't entirely combinational are the ones that actually have internal registers, like the instruction fetch issue, and that actually makes sense that would have that as an internal register. And in fact, it might make sense that we pull that register out of that unit and have the increment logic sort of outside of the instruction fetch issue state, because that might actually make sense for us, and that could be nice. I know, I'll be done soon. Oh no. Oh yeah, system bus, because we renamed that. So we got to do that now too. We need to remove the mem mapper, which is what I called it before. And we need to add the system bus. Xenowing RTL system bus. And yeah, all of the control logic for the inputs and outputs for these stages is also really trivial because we don't have any way of, we don't have any hazards or blocking or any of that kind of stuff. So this should be really basic. And I'm going to feel a lot better about having a smaller design for so many reasons. And then eventually we can go back and compare the two because everything's in Git. So that's really nice. But of course, this next stage, decode shouldn't be that bad. Execute Like, there is still some complicated decoding stuff, so we haven't really gotten to any of the complicated stuff yet. So we'll see how simple this actually stays. But yeah. No, I don't love it, Dark Second. I mean, I don't hate it, but I would like to have something simpler. And I don't feel at all embarrassed about doing it that way first. It made sense to me at the time, and now I know better. I'm proud of having learned. I also think it was a fun kind of experiment to try it that way, because it did seem to work. But I have seen the whole system stall, and I don't know if that's part of the system bus doing something wrong, or the CPU doing something wrong, or a combination of the two, which is what I suspect. And by redoing this, we should at least have a lot more confidence in the CPU implementation. So I think this should be good. So we've gone down like 2,000 logic elements, but remember, we're not really doing anything. So I don't suspect that this will be that useful yet. I think actually, though, with the analysis and synthesis, I think that's actually enough to be able to view the tool that I wanted to view, which should be the netlist viewer. Maybe I can't do that while it's compiling. We'll let it finish anyway. Yeah, Dark Second, this shouldn't be faster at all. In fact, yeah, it should be as slow. I don't know why it takes so long to compile. I mean, it is compiling a lot more complicated stuff than what we're seeing, mostly because, again, that DDRAM driver, or DDR controller, sorry. And that's where like all these memory bits and everything is too. I don't know why it takes so long, but it does. I guess some of the open source tools for some of the simpler FPGAs that are starting to appear are a lot faster. But I don't really know. Haven't tried them. But yeah, in fact, this might actually be slower because I think we end up with more CPU states. Because before, I think I had folded some of the states. Like I think I had folded the instruction fetch issue into both the write back stage and an initial stage. That's probably why I had that setup state. So we could kind of save a cycle there. And then I think I also saved a cycle by, of course, having the decode and execute baked into one, I think. So I think this will actually be slower. We'll see. But yeah, this is about 14% if I remember correctly. Now it's less. Quite cool. So wait for this a little bit. You can see again, this is also why I spent so much time on a ROM reloader, because changing the software should be much faster than this if possible. But actually, I've noticed with my ROM reloader, it still isn't very robust. So we're going to have to tackle that at some point too. And I have my own UART implementations as well, and I suspect something is stupid in there. Maybe we'll simplify those too. We'll see. In any case, here we have the xenowing. So this is absolute top level stuff. So the xenowing itself is actually here. And then in addition to that, we have the program ROM, and that's connected to the ROM loader, and the UART that's connected to the UART receiver. So that allows us to reload the ROM. And you can see here, we have a system software set coming out of the ROM loader, and that goes straight to this reset of the xenowing, which is combined with this signal, which is the soft reset out of the DDR controller, which I think was just like some intermediate between the actual DDR controller that's generated from Altera or Intel, and then the just the parts of the bus that I expect. So I think that's what that is. In fact, this this DDR controller has some stuff in it. That's not the part we're interested in. The program ROM obviously is just here we can see alt sync RAM. So this is a synchronous RAM component. The loader has some logic on whether or not it should reload. There's essentially a state machine here that watches for input from the UART, because the UART is just going to sit here and decode UART, and then output whole words at a time, or whole bytes at a time, I think. And then the ROM loader needs to have a state machine that just watches whenever there's bytes coming in, and then goes ahead and reloads the ROM. Because the ROM is actually a RAM, so that we're able to reload it, but it has initial contents that is our program. But anyway, in addition to that, we have the xenowing, and then we of course have these LEDs outputs, which is just some inverters that go straight out of the chip. Yeah, the UART UART decoder does seem compact, but I don't know if it's correct, so I'm not proud of that yet. Anyway, here's our xenowing, and of course that has this LED interface, and these are really simple because this is essentially just waiting for byte enables and write requests. The memory mapper will drive these if it decides that that's where the stuff goes, and then it has some registers for those. And then like this whole job is to keep the status or the register for the LED outputs, and also just be able to write stuff back, which is what this other register is. We can see the same thing for like the program ROM interface. It's really simple because it just decides whether or not the output's valid. I think it just registers that. And then the UART transmitter, this is just an interface to the transmitter. So this just says, yeah, not too exciting. Then we also have the DDR3 interface here. Oh yeah, we already went into that. And then the UART transmitter, which, whoops, didn't mean to expand that. Yeah, I think we already looked at that. Anyway, the fun stuff are the system bus, which is of course mostly just a priority decoder, and then the CPU, which is what we actually wanted to look at. So this is our CPU right now. And before we had this big core module that was really complicated. But now we have, of course, this. Oh, this is actually really cool to see, because we have here's our instruction fetch wait state, here's our instruction fetch issue state, and here's our decode state. I wonder if I can actually move these. No, I can't move these around. But we can see here, this is that register that's between the two, and that's all this is this register here, which is cool. And you can see the clock goes to that, and there's no software clear here, or soft clear, I guess that's what that is. And yeah, so then our instruction fetch state is absolutely trivial. Here's our adder or increment for the instruction counter, which just increments these relevant bits, it looks like, which is cool. It's optimized that a little bit. In fact, even the PC, it's gone down and optimized out these other bits, which is rad. And yeah, here we have if enable or the bus is ready, then we're going to load in this PC next. Or that's this mux on either the old value or the incremented value. And then we see, yes, here's the PC. Oh, it actually has separate registers, it looks like, for these low bits, because it's only incrementing the top, so it actually put that in a separate register. That's kind of fun. And then this just has a reset, which will reset these to 0. We could also tie those to 0, but I actually do want to have those bits here, because if, for example, when we do branches and jumps, I want those to at least have the full target address either feedback into this, or maybe we'll catch that as a trap. Not entirely sure how we're going to handle that yet. Who knows? Maybe we end up just tying these low eventually. So that's our instruction fetch, and that's obviously extremely simple. And then our instruction fetch wait is is this, which is exactly what we described, right? Because we described just that these are just pass-throughs, and so we see that exact thing here. That's so funny. And then we have the decode, which also does nothing right now. So that's funny. And then obviously there's this 32-bit register, and then the control logic, which is just a state machine. And in fact, that's what this yellow box is. And in fact, if we double click on this, we have a state machine viewer, which can show us the individual states and the transitions. And so here we have, it looks like, just because it's a very simple state machine, we have this idle or done. Actually, no, that's a different state machine. So control, this is the one we have. Here we go. And so here we have reset, which is this instruction fetch issue, and then we have this instruction fetch wait, and both of these can stall. So if those ready signals aren't valid, so that's why we have these loopbacks. And then decode, and we'll always just transition to this unless there's reset. That's what those are. And then execute just stays there or reset, and then error just stays an error or reset. So that's pretty sick. So this ends up being really simple, which is what we wanted. So I'm quite happy about that. Obviously, we haven't done anything very interesting yet, but yeah. Aaron the German says, does it give you a view which shows all the gates at once? At least it would be nice to show, for example, all of the CPU stuff at once. Because I don't really want to see this DDR3 interface. That's for sure. But it would be cool to see everything in the CPU. I don't know how to do that, actually. Yeah, I wish I knew how to do that. Yeah, thanks, Darksecond. I mean, the complicated stuff with that is also like the memory mapper, or now called the system bus, which is somewhat complicated and obviously a working memory controller. But we had those, and given those, we did, I think, have a successful instruction fetcher. Seems to work, at least for this one instruction. So yeah, I'm pretty happy about that. I guess it goes to show that if you keep stuff simple, it's easy. But yeah, I think that's all I'm going to do for today. Not really any point in running this on the hardware unless I set up signal tap and see the same signals that we see in the other one, but I don't need to see that. I trust that this is pretty straightforward. So I'm going to go ahead and commit this, and then we're going to call this a day. So let's do that quick. Probably going to get a lot of crap from Quartus, and that's fine. So now we're going to do git add RTL star for all that stuff. I don't know what this QWS file is. I've generally been adding all of this stuff. Just some user state, I guess. I'm going to add it just because it's all these Quartus files anyway. And then, yeah, we have this new, we updated the documentation. Looks like I made some changes in this other Quartus stuff that we don't care about, but this is fine. Go ahead and add Quartus. It's kind of annoying to have all that in repo, but at the same time, it's also like just easy to leave it in there. So I just want to look at these changes. So we do want to have all those changes in the make file. We did rename the system bus in the documentation stuff. I don't care about staging the fact that I changed which COM port I'm using on my machine. Don't need to do that comment. We do want to stage all deletions that we did. Don't need that. Good. Also, by the way, if you guys want to look at the repo, this is on a branch called new CPU. Because, of course, The old one still works, so I'm going to keep that around until this one is actually a valid replacement. But yeah, just so you guys know. But yeah, thank you guys for hanging out. I'm going to head out, and we'll definitely work on this next week. If I do anything between now and then, it'll be pretty minimal. But yeah. Anyway, thanks again, guys, and I'll see you next time.